Hi everyone. Today we are going to start angular momentum. So the first slide asks us, when do you have angular momentum? So it's a matter of perspective, and we're going to go more into this later. The first one, part A, we have a guy spinning in the air. Right? Does he have angular momentum? Yes, he does. Right? He is rotating. He has angular momentum. Then we have part B, right? This skater, after grabbing the pole, does she have angular momentum? Yes, she does as well. And then part C, this skater moving linearly before she grabs the pole. So assuming that she is not skating straight at the pole, right? If she is skating linearly as she goes towards the pole, she also has angular momentum. And it's not because she is spinning, right? Because she is traveling linearly, but it's because of the definition of angular momentum, right? You have to be a certain distance from an axis of rotation, and it's a matter of perspective, right? Is your angle changing relative to that perspective? So we'll talk about that, but it has to do with conservation of angular momentum. All right, so next slide, we have angular momentum of particles, right? We usually start with particles before we move on to the big ones. So what three pieces contribute to angular momentum? So the variables, right, that we are going to use for angular momentum, you have mass, you have radius, and you have velocity. Lo and behold, if you want to make something angular, multiply it by radius, right? So write three versions of the equation we can use to quantify this. So here we can see that this is r cross with p, right? If you want to, for example, when we talk about angular force, we call that torque, right? Because it's force crossed with radius, or more accurately, radius crossed with force, right? Because the order matters in a cross product. Now, here we have radius crossed with momentum to give you angular momentum. So some equations that we have here. We have L equals R cross with the concept mv, right? You could also say that is R cross with P that we already have in that image there. Next, if we aren't going to use the cross product, you would say that this is RMV sine theta, if that theta is right here, right? They use phi in this image, but that phi is the angle between the vector r and the vector p. Okay? So very similar to the concept with work and torque, right? Work, your cosine there is the angle between the force and the radius vector. With torque, your sine theta there, that is the angle between the force and the radius vector. Here, the angle between the radius and the momentum vector, that is the theta, that is the angle that you would use for that. Okay? Now, here is one more equation. This is kind of a shortcut. So if you have a perpendicular radius times mass and velocity, or if you have a perpendicular velocity relative to your origin, right? We'll go over a practice problem where we'll actually use that. But if you have this concept of a perpendicular radius, right? Say the radius is at a 90-degree angle from your origin, or relative to the motion, right? I guess that would be more accurate, relative to the motion. And then the velocity, if the velocity is at a perpendicular relationship. Okay, so we'll talk about that later. Now, what is L and its units? So angular momentum is essentially the momentum of an object relative to some origin that it is changing about, right? So it doesn't have to be rotating. So for example, this theta, there just needs to be an angle between your momentum and your radius. Okay, so if your radius and your momentum are parallel, no angular momentum. But as long as there is an angle between the two, you have angular momentum. So it's not just about rotation anymore. But is it usually a rotation that you're talking angular momentum? And the units for this are kilogram meters squared per second. Similar to what we had with momentum, right? Momentum is kilogram meter per second. Here you just add another meter because you are multiplying by that radius, right? So you've got the kilogram meters squared per second instead of a kilogram meter per second for your usual momentum. Now, number 4 says, y is your magnitude of L. Sorry, number 4 is y is L pointing up in this picture. So this is the right-hand rule, right? We talked about the right-hand rule before. When you have cross product, you take your first vector, say that is your R, so that's pointing this way. Your P is in the counterclockwise direction of your R, so that means your thumb L or your angular momentum would be straight up, right? Now, if that P was in the counterclockwise direction relative to your R, then your angular momentum would be downward, right? So you can use the right-hand rule to show that. When you have a cross product, right? When you have a cross product, you are going to have your two variables that you're multiplying or doing the cross product or the vector product of. Those two vectors are going to make up a two-dimensional plane, right? It's either going to be the xy, it can be the xz, it can be the yz, who knows, right? But those two vectors are going to make up a two-dimensional plane. Your resultant of your cross product is going to be in that third dimension. Okay. Now, if those vectors are three-dimensional vectors, then you've got just an infinite number of possibilities, right? That can be made up of all three dimensions at that point. But if you have just a pure two-dimensional xy, then you're going to have your L and the z. If your radius is now pointing off in all three dimensions, then that changes things. Same for your momentum. If it's in three dimensions, that changes things. But if R and P, or your two vectors in general, are just in the xy, then your L is in the z, or your resultant would be in the z. All right, now what is the magnitude of L if R and P are parallel, right? So that means that your theta would equal 0 and sine of 0 equals 0, right? So if they are parallel, then you are going to have no angular momentum. However, if your R and P are perpendicular, okay, right? If you have R cross P and they are perpendicular, that is just the absolute value of R times the absolute value of P. You can just multiply them straight through, right? So if they are actually perpendicular, then it's going to make your math a little bit easier. And we're actually going to use that trick right here. Okay, that is this trick. If if the radius or the vector or the velocity vector, if they are perpendicular relative to the rotation, relative to your origin, we'll talk about that a little bit later, then you can simply multiply that through. All right, so we've got a rotating system, right? Now, we have this mass 1 and mass 2. Looks like they are attached to a rigid rod. We're going to read that in a minute. But the question here is, does the equation work for systems rotating without translation? Do we sum up the momentum of multiple particles? So it's a good question. Is our equation going to work if they're not actually translating, right? If they are just rotating. So remember, translation is if an object is moving linearly. Right? I guess it doesn't have to be linearly, but an object is simply moving. It's scooting or rolling also is translation plus rotation, right? So let's look at this system. We have a light 1 meter rod, light meaning massless, joins two particles of mass 4 kilograms and 3 kilograms. The system pivots in the XY plane about the z-axis through the rod's center. The masses have a linear speed of 5 meters per second. calculate the magnitude and direction of the angular momentum. So if we look at this, we have a perpendicular radius, right? So we're going to use the concept of L equals R perpendicular mv, right? The radius is perpendicular to the velocity. So we have a radius of 0.5 meters, right? So our R perpendicular is 0.5 meters, and our velocity is 5 meters per second. Looking at the image, we can see that M1 is larger than M2, so I'm going to assume that M1 is 4 kilograms and M2 is the lighter 3 kilograms. Now, let's find the magnitude and direction of angular momentum. So we have R perpendicular mv. That means that they both have the same radius and the same velocity, so you can actually pull that out. You've got R and V times M1 plus M2. Okay, we would originally do M1 RV plus M2 RV, but the R and the V are the same for both objects. So we will take 0.5 times 5, so 2.5 times 7. Okay, I believe that is 17.5 kilogram meters squared per second. However, it asked us for the direction. So it tells us that this system pivots in the XY plane. Okay, that means that your vectors, while yes, they are constantly changing, it is simply in the XY plane. That means that no matter where these vectors point, they are never going to deviate from XY. So if you have R cross momentum, and it is counterclockwise, okay, you can see that rotation is counterclockwise. So the rule of counterclockwise still holds for angular momentum as well. Counterclockwise rotation, positive angular momentum, and that would be in the K direction. So to give the full answer here, you would say that is 17.5 kilogram meters squared per second in the K. So we kind of put it in component form, in unit vector format. So don't forget that the direction of angular momentum is in the K direction if it's in the pure I and J, right? Or I guess you could say in the pure X and Y, it'll be in the Z. If they have some axis of rotation, as long as that is uniform rotation, there's no complexity to it, your L is probably going to be in that axis of rotation. All right, last one here. This is where we're going to use that perpendicular trick, okay? So we have the angular momentum of a projectile. A particle of mass is shot with an initial velocity and angle above the horizon in Earth's gravitational field, as shown below. A lot of information there. Find the angular momentum about the origin. So notice this is not rotating, but we're going to say, what is the angular momentum relative to this point in space? Okay. So relative to the origin, what is the angular momentum when the particle is at the origin, at its highest point? So we have that information right here, right? That is at its highest point. And then C, about to hit the ground. Then D, why is angular momentum not being conserved? So we'll talk about that. But let's see, we have the angular momentum about the origin when the particle is at the origin, right? So we are going to use, I'm going to write out a couple of our equations. Okay. So we've got R cross P, R mv sine theta, or R perpendicular mv, which equals Rm perpendicular v. And we're going to go into this one now. So first, part A, we are at the origin. That means that our radius is 0 meters. In every single one of these is radius, 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 radius. If the radius is 0, then it's 0. So that means that your angular momentum is also 0 kilogram meters squared per second. So that one was pretty easy, just conceptual. If you are at your origin or at your relative point, right? So this would be very different if we said, find the angular momentum about the point the object lands. Then the object may have angular momentum at the origin, assuming that we include the initial velocity, right? If we're assuming that it's sitting at rest at the origin, no angular momentum because it's not moving. But if we assume that it has launched with that initial velocity, then it would have angular momentum relative to that point in space instead of the other one. All right, now part B, at its highest point. So we're going to use the perpendicular shortcut. So for part B, okay, we're going to use L equals R perpendicular MV, and I labeled this VB. I said that we've got VA, VB, and VC, because the VI, V1, and V2, that mixes two nomenclatures, I guess. It mixes two ways of explaining it. So you've got VI and VF, but then you also have V1 and V2, getting kind of complicated. So I'm going to call it V1, A, B, and C. Now, what we have here is that perpendicular R, right? If we can find the perpendicular radius of this object, right, we can find delta Y, right? So what we're doing here is we're saying that the perpendicular radius, let me get rid of that, the perpendicular radius here, okay, we are not going to use this radius vector. That is our radius vector, right? What we are going to use is this perpendicular radius vector, okay? So let's say, right, R perpendicular, bad perpendicular, is your delta Y, right? We can use kinematics to find delta Y, right? Delta Y here, let's see. I should probably go ahead and solve that for you, shouldn't I? I am going to use the kinematic equation of VF squared equals V naught squared plus 2A delta Y, okay? Here we can also make the assumption that A equals G, right? So if we want delta Y, I am going to change these so that we are consistent. This is VA and VB, okay? So what we're going to do here is we're going to say that VB, right, this is all in the Y direction, right? We have to split this between X and Y when we're doing kinematics. So VB in the Y, right, is going to be 0, right? Because the velocity at point B is purely in the X, and there's no Y component. So we're going to say that VB in the Y is 0, right? So if we want to solve for Y, we would say that this is, delta Y would be negative VAY squared divided by 2G. We also know that VA in the Y, okay, if we look at the launch, right, this is VA. Here is our angle theta, so this would be VAX and VAY. So here we can see that VAY equals VA sine theta, because sine theta equals VAY divided by VA. So I will make that substitution. We have negative VA sine theta, and that would be squared divided by 2G. Now remember, G is negative, so that's what's going to happen with that negative. Remember, G is a negative 9.81 meters per second squared. So if we assume that, then the negative is going to sort itself out. We were looking for r. So this is our radius, right? Our perpendicular radius is negative VA sine theta quantity squared divided by 2g. But now m is just m, right? It just says m. We're just using variables. But our VB, what would VB be? Well, we know from general kinematics, right, that if there is no acceleration in the x, then there will be no change in the velocity in the x, right? So the VAX in this projectile problem, because we're neglecting air drag, this is going to be constant. This is constant throughout the entire flight because there is no acceleration in the x. We are just in Earth's gravitational field, right? It mentioned that fact, which I thought was interesting, but that's why they did that, right? They mentioned that there is Earth's gravitational field, but we are not going to include air drag. So our VAX is going to be constant. And if VB is only in the x, that means that throughout the flight from point A to point B, the VAY slowly gets diminished down to 0, and then it's going to start growing negative as it accelerates downward back to Earth, right? But that VAX is going to stay constant. So if we see that cosine theta is VAX divided by VA, then VAX is VA cosine of theta, right? So our VB equals VA cosine theta. Okay. Now, if we are going to put that all together, right, then your angular momentum is negative VA sine theta quantity squared divided by 2g times VA cosine theta. I'm sorry, there needs to be an m in there. I forgot my m. Bingo, RMV. So that is your angular momentum at point B, or at its highest point, right? Now, you'll also notice that we didn't use any calculus for that one. We just used general kinematics. So if the problem is simple projectile, which we've already done, we had an entire chapter based on projectiles and general kinematics in the Y, right? The two-dimensional kinematics. If you can do the problem with kinematics and you can find the height and the velocity, then you're able to just solve it with kinematics. Now, part C says, find the angular momentum about the origin when the particle is about to hit the ground. So when our particle is about to hit the ground, what we're going to do is we are going to do the opposite of what we did here for part B, right? For part B, we used this equation. For part C, we will use this equation, the perpendicular velocity. Okay? So to find this is actually a really busy diagram, so let me get rid of some of this. What we're going to do is we're going to find the radius vector. Okay? Radius vector here. We will use the range equation to do that. Okay? But then we are going to find the perpendicular, whoops, that's too long. The perpendicular velocity vector. Okay, just like here, we had our, oh goodness, let me carefully draw this. We had our perpendicular radius, and then we crossed that with our velocity. Here we're going to take our radius and use the perpendicular velocity. So similar concept, just something that we haven't done yet. So the radius, okay, we use the range equation. If you do not know the range equation, oops, range equation. This is interesting and important to know in physics, right? In in kinematics, your range, if you assume no air drag, the range of an object is v naught squared of sine 2 theta divided by g. Right? Divided by g. Now, to put that in terms that we are going to use for this problem, that would be VA, right? Because we're saying VA is our initial. So that, right off the bat, L equals RM V perpendicular. This is our R vector. Okay? We're just going to use VA squared sine 2 theta over G. Okay? Now, for our V perpendicular, okay, what we can say is that VC is negative VA, right? That's fine. However, because you're not wrong. But what would be even better is to say that if you have VA, VAX, and VAY, it would be even better to say that VC in the Y equals negative VA in the Y, right? Because we know that if you throw an object, if an object is launched upward, even in a projectile, right? Once it returns to that original height, that original vertical level, it will have the exact same velocity component in the Y direction. Okay? It's the same as if you threw it up and came right back down. The projectile only knows gravity in the Y direction. So if we're talking in the Y direction, VC in the Y equals negative VA in the Y. And we know that VA in the Y, we already solved that. That is VA sine theta. So this VC in the Y, which is what we're doing here, right? We're just taking VC and we're getting its Y component, right? So that would be negative VA sine theta. So what we'll do then is take our range, which is VA squared sine 2 theta divided by G times mass times negative. I'm just going to pull that negative out and put it up front. Negative. Then VA sine theta. Now remember, you cannot do any math finagling with sine theta and sine 2 theta. Okay, you can't just factor that 2 out or something. So that's we're just going to leave it as it is there. And that is your angular momentum about the origin of a projectile as it is about to hit the ground. Okay? Now our last part, okay, this is marked important. Why is angular momentum not being conserved here? So this is important. I will actually write this out. What's happening here is that gravity, which is an external force, okay, gravity, okay, this is an external force acting on this system. Okay, this is creating torque. And just as a sneak peek of what's to come, if you have torque on a system, this is going to change your angular momentum. Okay. So that's where we're going to call it for this set of notes. Okay. All right, that's it for this video, and we will continue on with angular momentum in our next video.